Hello students, in this video we'll discuss some elementary properties of the gamma function via its product formulation. So let's recall, we just proved that gamma of z, the gamma function, as we're defining it with a product, is e to the negative gamma z over z times the product, n goes from 1 to infinity, of what? Of 1 plus z over n to the negative 1, e to the z over n, like this, right? And we're here, gamma was this euler-mascheroni constant. Gamma was the limit as n goes to infinity of the nth harmonic number, so 1 plus 1/2 plus 1 over n minus the log of n. That's the euler-mascheroni constant. Again, we don't know much about it at this point in time, which is sort of remarkable. And then what? And then let's sort of do a little bit of algebra with this to get the Gauss formula. To get the Gauss formula, what do? We're going to write this as I'm going to write this as a product, right? So I'm going to write this as e to the negative gamma z over z times the limit as n goes to infinity. The product, k goes from 1 to n, and then I'm going to multiply this out. So I'm going to turn that n into a k. It's going to be k plus z over k to the power negative 1 e to the z k. Now I can bring this term over here in to the product, and so this is the limit as n goes to infinity of just the product. K goes from 1 up to n. Then I'll have a k, and then a kz. K plus z times z, right? Times z, good. And then e to the z over k, 1 over k. And I'm going to subtract off a gamma from this over here, like that. Okay? Good. And so now what can we do? Now, of course, we can sort of cancel these things out over here and conclude what? And conclude, well, what are we going to get over here? These terms over here are going to give me a k factorial. Okay, so we're going to have a k factorial, an n factorial rather. It's the limit as n goes to infinity of n factorial, all divided by what? I'll have a z plus 1, z to the plus n like that. Good. And then what's left over here? What's left over here is just going to be z to the what? Oh, it's going to be e to the z, and then I'm going to subtract off a log n over there. So that's just going to be an n to the z, because I'm passing the limit. What's happening? All these harmonic numbers are canceling out over here because you're producting them, right? So those cancel out with these guys over here. And you're just left with a log n. So you're going to have a log n to the power z like that. And that gives you, this is the Gauss formula. So this formula is called the Gauss formula. For the gamma function. Okay, excellent. And this Gauss formula gives us a lot of useful information, right? What's the first thing it gives us? So this is a representation over here for gamma of z, right? Let's look at gamma of z plus 1, right? What's gamma of z plus 1? Gamma of z plus 1 is going to be what? Well, it's going to be the limit as n goes to infinity of what? Of n factorial, like that. And then z, n to the z plus 1, right? All divided by what? Z plus 1, all the way down to z plus n plus 1. Good. And now what can I do with this? With this, I can plug in a what? I can replace, I need a z over here, pull an n out, right? Pull an n out. Then I have to pull z out as well, right? So if I do that, what's going to happen over here? If I do this, we can write this and say that this is going to be what? I claim that this is going to be equal to just z times gamma of z. Let's figure out how the algebra has to work for this. The algebra has to work as the following. This is saying, is this equal to z times the limit as n goes to infinity of what? There was no z there, so put a z down over there, z up top there, and then reindex everything, right? So that's exactly how it goes. So we're just going to reindex everything, so let's just leave it like that. So we just reindex everything by reindexing. Excellent, okay. Okie doke, so now we can replicate this, right? So now iterate this. If we iterate this, what's going to happen over here? If we iterate this, we're going to get the gamma of z plus n is going to be gamma of z times what? Gamma of z times z, and then z plus 1, all the way down to z to the plus n minus 1 over here. And oftentimes this is written the following way. This is written in the reverse order. This is written as gamma of z is equal to what? Is equal to gamma of z plus n divided by what? Divided by z and then z plus 1, all the way down to z plus n minus 1, okay? Now, why is this useful over here? Because we know that gamma has simple poles, right? Gamma has simple poles. So since gamma has simple poles, we can compute the residue of gamma at the point negative n, right? It'll just be the limit as z goes to negative n of z plus n times gamma of z, right? Excellent. And so now what do you do with that over there? What you do with that over there is you say, okay, well now I can compute this easily. I should put a gamma of z plus n up here, right? And so now what do we see? If I plug in negative n into this formula over here, what we're going to get negative n factorial over negative 1, right? So using this formula over here, I can use this formula over here to write that what gamma of z is times z to the n. And so what this will give me is this is going to give me let's think about a negative n plus 1, all the way down to negative 1. That's a negative 1 to the n over n factorial. So that gives me the residues of gamma. So I found all the residues of gamma, which is a very useful thing now, because what is the next thing we want to compute? The next thing we want to compute is the logarithmic derivative of gamma, right? And so what would the log of gamma be? So the log of gamma is going to be what? Well, the log of this thing is going to be negative gamma z, plus the log of 1 over z. So the log of 1 over z is minus the log of z. And then plus all these things over here, so then plus the sum. N goes from 1 to infinity. Then you have the log of these expressions over here. So what will these expressions give you over here? They're going to be an n plus z, so you're going to have a negative log. This is really what? Like a negative log. So these things over here, of course, just give you z over n, right? Z over n. And then minus the log of 1 plus z over n. That's the log of gamma. And so what's gamma prime over gamma? This tells you that gamma prime over gamma, what's the logarithmic derivative of gamma? It's just going to be negative gamma, and then minus 1 over z, and then plus what? And then plus, that's going to give me a 1 over n, the sum. N goes from 1 to infinity of 1 over n. And then this thing over here is going to give me a 1 over z. It's going to give me a, let's see, it'll give me a n plus z over n. The n is going to cancel out, so I get no n plus z. That's going to be 1 over n plus z. 1 over n plus z with a minus sign. Okay, beautiful. Now the kicker with this is, let's think about this for a second. What's going to happen if I was to do the second derivative? So of course I have to simplify this expression over here, right? But let's think about what's going to happen. If I was to do one more derivative, this is what's going to happen. The derivative of gamma is going to be nothing. That's going to be positive. And the derivative of this thing over here, as we can check, is also going to be positive, right? So this calculation is going to allow us to conclude that gamma prime over gamma prime is strictly bigger than 0, which says that the gamma function, okay, so in other words, if we did the calculation, we'll see this, right? It's going to be n plus z over n minus 1, right? Minus n over 1, n times n plus z. And then we do the derivative of that, we're going to get something non-negative, right? So we're going to see exactly how this is going to work. So this says that that gamma is log convex. So gamma is a log convex function. Since gamma is a log convex function, the Bohr-Malrup theorem is going to tell us that the only log convex function that has this particular property over here, this cycling property, and a value of 1 has to be the gamma function, which we'll prove in a further video. Thank you very much.